Hello and welcome back. Okay, it's a big day today. I am converting the last of the breadboards, which are part of the core processor, to PCB. This is the ALU result module, which performs an add between the left-hand and right-hand sides of the ALU and asserts that onto the bus as necessary. I've got the Fibonacci sequence test code loaded up, so let's give that a go just to check that everything's currently working. Okay, well that's worked perfectly. Now the core functionality of this system has been spread across a whole bunch of different videos, so I will give a basic outline of what's going on here. Now the core functionality is these two 4-bit adder chips, which add together the two inputs. Then we've got a line driver that can conditionally output the result back to the main bus. We've got a latch chip in here, which is storing various flags and some configuration bits between cycles. And then we've got a multiplexer chip here, which is being used to control what the carry input to the adders is. Then the rest of this is some logic which is generating flags. Now we have made some of this wiring redundant, so those were carrying the control lines down. That is the 4 bits of logical operation selection. So that's the ALU clock. It's not being generated here anymore, but it's actually coming back from the output here to drive this board. That was the system clock, so we shouldn't need that anymore. That was logical carry, which gets stored in the latch along with other flags. So they were producing the logical combination as part of generating the ALU clock. So that was ORing together them all. But that was two input OR gates. Okay, so 2 of these 283s are going to be the core work. I need a 574 latch chip for storing some bits between operations, and a 541 to push data back to the bus. And obviously we want some LEDs. That will output the result to the main bus when we need it to. That will display the result for us. Now we need to generate it. Right, so this 574 latch chip is clocked by the ALU clock, because the ALU control outputs the 8 control lines during ALU dispatch, but the result section doesn't use them until the next cycle when the ALU is going to complete. So they get passed through this latch chip so they're actually ready when we need them. Then these fast adder chips are going to do all the real work. Right, so these A inputs are from the shift unit. B inputs will be from the logic unit. And the result is the output from these. Carry out of this lower one goes to carry in of the upper. Okay, so arithmetic carry out, that's going to go to another one of our latch inputs. And we actually had a second line driver that we were using to buffer all of our flags. On the breadboard, it's the second line. We may want to reorder these a bit for routing convenience. So the first flag in the display we've got at the moment is logical carry. So I'm just going to feed that through one of these, just so we can guarantee a nice even brightness. Okay, so arithmetic carry in, that was generated by a selector. So the output from this is that arithmetic carry in. Now we just need to select the correct 4 input options for carry. First one's simple. Option 0 is 0, so that's ground. Option 1 is the carry flag from the last operation. Option 2 is a 1, so that's used for the increment ops. And then that one is also 0 because it's not currently used. Okay, so now we've actually got the core functionality of the ALU result function working. So we'll add the numbers together using the appropriate carry flag. Now all we need to do is worry about the other 3 flags and displaying them. The first flag we want to generate is the 0 flag, which is simply all the bits in the output are low. Now we could actually generate that in a single hit if we had an 8 input NOR gate. But what we can get is a quad 2 input NOR gate. When we're routing these, it'll be worth remembering that we can put these in whatever order we want. Now to merge the outputs together to make one big NOR gate, we want to AND them together. Now I'm actually going to drive 2 of these line driver inputs, because I can actually pair these up to drive the LEDs and the output lines differently. So here the generated 0 flag is going to drive the LED and the main flag output for 0 from different channels. Okay, next flag is going to be sign. That one's really simple because that's just the top bit of the output. In 2's complement mathematics, this tells us if the result is positive or negative. Okay, so the last flag is overflow, and that's going to be a complicated one. Okay, to understand the overflow flag, you want to be watching video 33, but it works by comparing the signs of the 2 inputs with the sign of the output and checking to see if it's a combination that's valid. Now, firstly, we need exclusive OR gates. So we take the signs of the 2 inputs, exclusive OR that with the sign of the result, and then we AND those together. And we just happen to have an AND gate up here. Well, I don't have 2 lines here, but this is only driving 1 output. Okay, we've done that pretty efficiently. We've got 2 gates spare here, and we've only used 3 of the inputs up here. think maybe we should just keep our lives simple and use one of these. Anything else is adding an additional chip to my BOM, and I don't want to do that. Mixing the resistor types for the flags doesn't feel right, but I've got 5 flags and the resistor arrays only come in 4s. Okay, so we want a decoupling cap by all of these, plus one larger one for the board. Don't like leaving half a chip unused. Okay, I think that should be done. Ah, look, wrong LEDs. Ah, look at these nicer devices with the annotation on to show which way round they go. Okay, I don't like the way that happens. Right, now putting the output line driver up there is the obvious choice. I think putting the flags in the top right up here is obvious. I think swapping these lines over suddenly makes more sense. Potentially move them down here as well. Look at that, suddenly get neater. Awesome. Okay, I think the arrangement here is pretty good. Actually, I want an LED for when we're asserting to the bus. Now ALU assert is active low, but if I feed a 1 into an input of one of these spare XOR gates, it becomes an inverter. Yeah, I think that's a good layout to start routing. Okay, getting the data lines to the adders and then on to the output is probably the trickiest job remaining. So let's attack that first. Now NOR gates here, they don't need any specific mapping to the result bits, so I could reorganize these to make it easier to route. I could just as easily have swapped these two inputs over. In fact, that's probably what I should do. I need to label this resistor better. I usually like to minimize the labeling where it's obvious what it is, but that one looks too much like the caps it's close to. Alright, I don't see any rat tails on this side now. I need to make sure I connect the grounds up because I don't want this splitting it in two. Not a lot of traces left to do, but some of these aren't particularly easy. There you go, last trace. Now let's have a look. 5 volts. That's pretty reasonable. And that's pretty terrible, but it is going to have ground fill. Okay, let's get the ground fill plane on the back. Okay, there were a few tight bits in that, but for the most part, this was actually a pretty easy board with quite a lot of space. Glad I did manage to get those two 574 latch chips on the shift unit and the logic unit. Otherwise it would have been quite a tight squeeze on here. Okay, I'm very keen to see this one. That's going to look cool. Okay, I'm going to collect my components up and get my soldering gear out, and let's get this done. I actually got some different solder paste. Now, the stuff I used last time was actually lead free, and that led to a couple of joints being a bit more tricky. I ordered that stuff by mistake. So I've got some temperature stable leaded paste, but this time in a syringe. Okay, this stencil doesn't want to lie very flat, so I'm worried about getting some squidging underneath it. These resistor arrays are by far the most difficult thing I solder. Okay, this capacitor pad seems to not have very much paste on it. Fortunately, they're very forgiving. Okay, this should be a 574. So that holds the values of the flags between clocks, whereas the 5-4 ones are line drivers. So this is the most important one, that actually outputs the value from all the ALU computation onto the main bus. The 153 here is selecting the source of the carry flag. Okay, these pads have basically no solder paste on. I have to watch that one carefully. Actually, maybe I should have tried squeezing solder paste onto the pads directly. Might have been easier. It's going to be easier if I can turn the boards around for the LEDs. Okay, I think that's everything. That's the one we have to watch. So I was asked the other day why I've started cutting pin headers before I hot air the board, and the answer is very simple. I'm waiting for the hot air to warm up. I was a bit worried when that first capacitor jumped out of space, but those resistor arrays seem to have been pulled perfectly into place. Okay, I'm going to check the video on there because that doesn't feel like there's much solder paste on the pads. There's a few of the pins on here and a few of the pins on this chip didn't look like they flowed. Fortunately, we have a very simple solution to that problem. And to be honest, I like the way that solder paste behaved in most places, so I'm more inclined to think that was down to bad solder paste placement with the stencil. It was bending a little bit. This new paste has handled the resistor arrays really well. Okay, let's get the pins on. Now that is beautiful looking PCB. Let's hope it works. Okay, so let's double check this all still works. A few things have changed since I last ran the Fibonacci code. That looks correct. Now that belongs there. Wow, there's no breadboards. What are the odds on this working first time? Okay, that's pretty promising. That's not though. Okay, that looks like the string print operation isn't working right. Okay, so we've written E out. Now the next thing that gets loaded in is going to be a 0, hopefully. I haven't got the assembly language in front of me. I think that just read the 0 in there. And that's performing an AND operation, so that's the test. It's outputting 2 zeros. That doesn't look like a 0 there. So expecting all the inputs to be 0, which they are, but then we're expecting the 0 flag to be set, which is what's going to modify the code action. Now I'm assuming that I got the wiring right between those. But that is the first bit. So I suspect an issue between the carry out from the first adder to the carry in of the next. Okay, so that looks correct. It's low, but that's floating. Pop this out and have a close look again. Okay, that looks like that pin has no solder on it. Okay, I imagine half of you spotted that when I was inspecting. More like it. Okay, that's not complete. Did I ever update this code to support high-speed output? No, that wasn't right. This is something as simple as a nav joint I've missed. This looks like it's moved off spot, and I can't see if I've got good contact on these connections up here. Now, I don't know whether or not they properly reflowed onto there. So I'm going to touch these with my soldering iron. If this doesn't work, I may need to spend a bit of time writing some diagnostics. But of course, most of the function of the ALU just does come from these adders. So if we're getting the right result out of there, then that's most of the way. 0 flag is by far the most commonly used flag. And if that's generating the right value, that would explain why a lot of the basics are working. But then Other operations like the carry flag rely on this 574 to hold the data between operations. So if that wasn't soldered right, it would explain it. So much has to be working to get this far. So it's at value 7, which is where it goes wrong. Okay, what I'm doing here is stepping through the code several times until I work out exactly where it goes wrong. And I actually found it was calculating the Fibonacci numbers correctly, which isn't that surprising because it's just simple adds. But it was going wrong during the divides to turn the binary representation into decimal. So then I wrote some simple test code that just called the divide operation directly, so I could step my way through that code multiple times until I worked out where it was going wrong. And it turns out that the logical carry wasn't working. Then I discovered that the logical carry hadn't been handled. In the original schematic layout, you'll find this is a ground line. I don't know how that happened, but the lack of that line caused me to miss latching the data, and so there's no connection from the logical carry out from the shift unit back into the logical carry line. So I need to implement this circuitry. Now this pin I had accidentally assigned to ground, so in order to bodge this, I'll need to cut this away from the fill, connect it into one of the several unused lines on the 574, and then take the output of that to the logical carry line. Unfortunately, that's very nearby because I was passing it through this 541 in order to drive the LED. Let's take a look at that. Okay, now let's see if I can bodge this. Okay, what I need to do is disconnect this bottom right pin from ground, because that's where the arithmetic carry comes in. Then I need to wire it into this pin and wire the output here to the nearest location where the arithmetic carry is present, which is that pin there. This is going to be difficult, but not impossible. Now this would be totally preferable if I can do it without having to desolder the pin. I don't think that's going to happen. That might do it. Okay, well there's still a connection there. Okay, I've got to watch that nearby line. Okay, that was unintended. Okay, I think we've actually managed to disconnect that. Wouldn't be too bad to replace these pins. Let's see if I can straighten them. Now, I fully intend to replace this PCB with a fixed one, but if I can bodge it into working, it lets me get on and also reassures me that the rest of it is okay. Right, so this third pin along is the one we're interested in, and that's currently tied to ground, and it's going to be really difficult to try and detach everything in that pad around there. It's surrounded on all four sides. I'm going to see if I can just lift the pin up. This would be potentially a lot easier if I desoldered the whole chip, bent the pin and then brought it back. That's got it. Okay, so in theory, so that's the arithmetic carry in going into one of the latches. So now we just need to connect the output from that latch to this pin here, which is the nearest location that we've got the arithmetic carry output in. Very convenient here, but I decided to use one of the spare lines in this line driver to improve the LEDs. I had a perfectly shaped piece of wire there, and it's done a runner. Said I think it might be a whole bunch easier if I trim the wire down after soldering the first side. Okay, let's see if we can get this line in. Need an extra hand. Right, so I'm going to try and hold this in place with a little bit of Captain tape. Okay, that actually looks good. Now, my big concern here is that this wire is very, very short, and it's possibly going to heat up enough to destabilize the joint at both ends. I think that's got it though. That is not pretty, but I'm hoping it will let us test the rest of the circuit works. Let's give this a go. Right, so this is still the test divide in here. That's not right. Hang on, we were doing 95 divided by 10. So the remainder is correctly 5, but this shouldn't be 0. Okay, so we're into the divide function, cool. Now the basic function is we're going to shift this value up, and we won't see any change until this is greater or equal to the number we're dividing by, which it is now. Now two things should happen. We should be subtracting this from this, but we should also be incrementing this via the carry flag. So that's the subtraction. So we've got a result of 1 here, which is correct. Now we're on the add with carry, which is basically add with carry b comma b, so that's basically just adding the carry flag into this value, and that's the bit that's not working. So carry select for the next operation is 1, so 1 should be previous carry. 1 0, that's right, but that hasn't worked. So we added 0 with 0 and the carry flag and got 0. Okay, now could have wired this 153 wrong. Oh, I know what this is. So this is the least significant bit here, currently 0, but I bet you, yeah, that pin is floating. So that's the wire I thought I scratched, but I've actually broken the connection. Let's hope that's all it is. Yeah, so you can see that I did scratch along the trace, but that didn't look to me like it was enough to break it. It's far easier to break a trace by accident than it is to do it deliberately. The tiny little bit of scratch there. So that goes to that pin. Might actually be slightly better if it went under. Okay, that looks like I've got a joint. Now I've broken one of these pins. don't know if I captured on camera very well, but I did actually bend a bunch of these while I was trying to cut the tracks here. I wouldn't be happy with that for a permanent one, but I'll be replacing this as soon as possible. Okay, now we're going to be third time lucky. That looks like we got the correct result. That's 9.5. Okay, that works. This will give a bit more of a stress test of the ALU. Okay, I jumped straight in there. That's the correct final answer. And if we really want to test the ALU out, accept no substitutes. Right, speed it up. Okay, 7699 is indeed prime, and 7703, 7717 and 7723 is the one after. That's a very good sign. I'm just letting it run at max speed through to completion, which will be the highest prime numbers you can fit in a 16-bit value. Yes. Right, so far as I can tell, this is fully working, and this is the first time we've had a fully operational CPU without any breadboards involved. I am really pleased with this. I was very worried for a while there that I was going to have to do a new PCB before I'd get this far. I don't even know what to say at this point. This is actually a really big milestone in the CPU. There's very little left to be done in terms of the core CPU, just a little bit of refinement and some bodge removal. I do want to sort out the additional RAM for the memory module. Once that's done, and once these bodges are removed, I want to do some experimentation on just how fast we can clock this. So we've had it up to 2.5 megahertz before, but I think we can go faster than that once everything's right. But I'll get rid of the bodges before we worry about that. What's really cool now is I have a whole bunch of space back I can use to put breadboards in to start refining the circuit, and I can move things around because I'm not quite so tied to where I'm going to plug stuff in. So sort the RAM out, a little bit more PCB work on the side, but the next big project to start, and that's going to be very soon now, will be the VGA display. Okay, well I hope you found this interesting. I'm really chuffed with this progress. It's one small board, but it's a big step forward on the build. Hope you found it interesting. I will see you again soon. Goodbye.